this way, and your slides are all queued up. Tony's doing double duty streaming on YouTube. We have a separate teleconference line with the NASA Teleconference Center.
Welcome to the Hubble Science Legacy Teleconference. At this time, all participants are in a listen-only mode until the question and answer session of the conference. At that time, if you would like to ask a question, you may press star, then 1. Today's conference is being recorded. If you have any objections, you may disconnect at this time. Your host for today's conference is Ray Villard, News Director of the of the Space Telescope Science Institute. You may begin.
Well, good afternoon, everyone. Greetings from the Space Telescope Science Institute in Baltimore. On behalf of everyone here, I'd like to welcome our reporters to the Science Writer Telecon, Hubble Science Legacy through 2020. Over the past quarter century, Hubble has probed the universe both near and far, and has unveiled wonders that were once only left to the imagination. Besides being a scientifically productive observatory, Hubble's discoveries and images have made the telescope Hubble a household word. We have a panel of distinguished astronomers here attending a week-long conference workshop reviewing 25 years of Hubble and looking ahead to what Hubble will be doing for the remainder of its operational era. They will cover some of Hubble's key accomplishments and its synergy with the next generation of space telescopes. At the conclusion of all the presentations, we'll take questions from news media. With that, I'd like to introduce our first speaker, Dr. Amber Strong, who's an astrophysicist at NASA headquarters. Amber?
So this year, the world celebrates Hubble's 25th anniversary. And that's no exaggeration. The entire globe is celebrating this anniversary. So we here at NASA know of over 100 events just in the US that are being planned, 60 or so events in Europe, and there are countless others across the world that we don't even know about or we're becoming more aware of day by day. And so it's really not an exaggeration to say that the globe is celebrating this anniversary of Hubble. And so Hubble has, through the years, of course, changed the way that we as scientists understand the universe, and it's really captured the public's attention. It's captured the imagination of the public due to the beautiful images that it's released, and also to the very human story that Hubble has had over the years. So Hubble actually marks a really critical time in NASA's history when science and human exploration work together for the first time for a common goal. And that part of Hubble's story is one of the reasons I think that it sticks so much in the public's attention, is the fact that, you know, the Hubble story is very much a human story, in that when we launched the telescope, of course, everyone's aware of the fact that there was a flaw. And so astronauts had to risk their lives to go up to Hubble and fix it. So over the last 25 years, 33 astronauts have risked their lives to deploy and service Hubble and to make Hubble what it is today. So after the last servicing mission in 2009, Hubble is better than ever. It's working great today, and we expect it to continue working out until 2020 or maybe even a little bit longer. And so just glad to have everyone with us this week as we celebrate this historic anniversary of the NASA and ESA Hubble Space Telescope.
Great, thank you, Amber. Our next speaker is Dr. Ken Sembach. Ken is Interim Deputy Director here at the Space Telescope Science Institute and formerly head of the HST Mission Office. Ken?
Thanks, Ray. I'd like to just say thank you to everybody who's listening in and joining us in this week of celebration of Hubble's 25th anniversary. As Amber was saying, the observatory is in remarkably good condition and better than ever. In the last 5 years since last servicing mission, the telescope has been performing extremely well. The instrumentation has actually been getting better with time, in the sense that we've been able to calibrate it better and know more about how the observatory is performing. All of the subsystems on the observatory are performing well. 5 of the 6 gyros that were installed during servicing mission 4 in May of 2009 are still operational. The one that failed last year in March of 2014 failed in a way that was completely expected and on a time scale that was expected. So in that sense, Hubble hasn't given us any operational surprises in the last 5 years, which has been a good thing. It's also worth noting that 2 of the instruments that were repaired during that servicing mission, the Advanced Camera for Surveys and the Space Telescope Imaging Spectrograph, are both working 5 years here after the servicing mission, which is longer than they worked originally with their original electronics. And so we have great hope that, in fact, these 2 instruments, along with the 2 that were installed, the Cosmic Origin Spectrograph and the Wide Field Camera 3, will continue to be operational for several more years. We have a 2020 vision for the observatory on the operations teams that allow us to get out to 2020 and provide at least 1 to 2 years of overlap with the James Webb Space Telescope, which will be launching in late 2018. The combination of these 2 observatories will be very powerful scientifically, and together they'll certainly be better than they would be on their own. They'll be able to follow up on each other's discoveries and will surely unlock some more secrets of the universe that we don't know about now. In the few moments I have left, I'd just like to say that it's been a great 25 years the observatory is doing science now that was never envisioned, and it's doing it in ways that was never envisioned, whether it's looking at the atmospheres of planets around other stars, or reaching out to the most distant galaxies in the universe, or watching stars explode or form. Hubble is doing that now in ways that we hadn't originally envisioned, and for which we're grateful to have an observatory that's able to do that.
Great, thank you, Ken. And with that description, let's get into some of the very cool science Hubble has done. And for starters, we're going to start close to home with the solar system. And our guest is Dr. Amy Simon from NASA's Goddard Space Flight Center. She's used Hubble for the past 20 years to study the planets out there. Amy,
Thanks.
it's all yours.
Thanks, Ray. Yes, I've used Hubble pretty much my entire career, and it's hard to believe that it's been 25 years. It doesn't seem like it's been that long. But Hubble has really been pivotal in our solar system exploration, and a lot of folks might want to know why we would need to use Hubble when we can send a robotic mission out into the solar system. But the reality is that it's actually very hard to do, and we can't do it as often as we'd like. And Hubble's been sort of our premier observatory to help us refine those science questions before we launch a mission, and to make sure that we know what we're going to find when we get there. And one example of this is for the New Horizons mission, which is on its way to Pluto, and it's due to arrive this July. And before Hubble really came on the scene, we knew about Pluto, and we knew it had a large moon, Charon, almost its size. But Hubble actually discovered quite a few other moons, 4 more moons in the meantime. So we now know that Pluto has 5 moons, Charon, Hydra, Nix, Kerberos, and Styx, and also a fairly substantial dust environment. So the Hubble observations have helped us better plan that mission, to know where it's safe to cross through and what we're going to find when we get there, and also that there's more targets to look at besides just Pluto and Charon. But in addition, another objective of the New Horizons mission is to go on into the Kuiper Belt. And when we launched that mission, we had no idea if there was going to be an object we could go to. And so one of the big results from Hubble has been a search looking for the New Horizons' next target. And we now have 2 candidate targets. The extended mission is under discussion now to see if it'll be approved. But we know that there's a place for it to go, and that's entirely due to Hubble. But moving in a little bit closer to home, really Hubble's been a premier weather observatory as well for the outer planets. And my particular interest is in studying Jupiter, and we've been able to observe real-time events happen in the atmospheres of these planets only because we have Hubble. And one example of this are impacts that we saw in 1994 and again in 2009, where you could look at the leftover debris from comets or asteroids that had hit the atmosphere. But we can also watch literal changes in the weather, where parts of the planet change color very, very rapidly and without explanation. And now that we have a 25 year time base of observations, we can begin to understand what drives those changes on the planets, and which parts are seasonal and which parts are not. And so that's actually helped us quite a bit to understand how these planets actually serve as a laboratory for fluid dynamics. They help us to understand a little bit better some of these same processes on Earth, with a difference in seasons, a difference in tilt, and without land in the way to change the weather. So we've been using this kind of as both a laboratory and an observatory at the same time. So that's been sort of an interesting aspect of being able to use Hubble. And then one other interesting result is that one of the missions we'd like to do is to a large moon of Jupiter called Europa, where it's suspected that there's a liquid water ocean beneath the surface. And some recent observations suggest that there might actually be water plumes coming out of Europa, similar to what we see at Enceladus at Saturn. And if this is true, that actually would help refine the missions that we might send there. We would use different instrumentation, we would target the areas differently, hoping to understand more about these plumes and whether we have direct access to the ocean. And so Hubble has really been pivotal in both keeping our missions successful and helping us plan the next generation, and then doing scientific discovery in its own right.
Okay, thank you, Amy. When Hubble was launched, we knew about 9 planets. Now there are, 2,000 or more. And Hubble really wasn't designed, because we didn't know about planets back then. Dr. Jacob Bean from the University of Chicago has used Hubble in very clever ways to study the atmospheres of planets orbiting other stars. Jacob.
Thanks, Ray. So it's very exciting to be here to celebrate the 25th anniversary of Hubble. As Ray mentioned, before Hubble was launched, we didn't know about planets around other stars, but since then, thousands of planets have been found. And so really the key to understanding this diversity of planets that's been revealed, I think, is studying the atmospheres. And so this is a way that Hubble has really transformed the study of planets beyond our solar system. It's by studying the atmospheres of those planets. So on the next slide, you can see how the techniques, a summary of the techniques that Hubble has used to study exoplanet atmospheres. The primary way has been using planets that transit their host stars, that is, eclipse their host stars, pass in front of their host stars once per orbit. And this is a really fascinating laboratory for studying planetary atmospheres, because before these transiting planets, we have multiple diagnostics of the planet's atmospheres. During the transit, when the planet passes in front of its host star, we can see some of the starlight filter through the outer limb of the planet's atmosphere, and the chemical composition of the planet's atmosphere is imprinted on the starlight. Also, for planets that transit, they also go behind their host stars, and you can see the stars block the lights that the planets emit. So that's a fascinating view to the thermal structure and the temperature of those objects. As well as looking at when planets pass behind their stars, if you observe them while they orbit their stars, you can see the changing face of the planet presented to Hubble. And you can map the temperature of the planet not just on one side of the planet, but all the way around. And so recently Hubble has started using all of these different diagnostics of transiting planet atmospheres to learn more about these objects and put the enormous numbers of planets that have been discovered around other stars in a broader context. Some of the themes that have emerged over the last few years are measuring water abundances to trace the formation of planets. So on the next slide, you can see some of the results that have started to come up. Water is an interesting molecule to look for in planetary atmospheres, because we think that traces the formation and evolution of planetary atmospheres. And so recently, my team has been able to make a precise measurement of the water abundance in a planet's atmosphere for this planet known as WASP-43b, which is shown on the figure. And what we've been able to do is make a quantitative now comparison in the enrichment of heavy elements in the planet's atmosphere and compare those to what we see in the solar system. A fundamental trend seen in the atmospheric heavy element abundance in the solar system planets, the giant planets, is that you have more of these heavy elements as the planet becomes smaller. And so this planet, WASP-43b, which is 2 times the mass of Jupiter, so that extends the range of planets that we can see in our own solar system, follows that trend. And so over the next several years, we expect to use Hubble to measure water abundances and fill up this diagram and make these quantitative comparisons to the solar system planets for about 15 to 20 other planets. The other theme that's emerged recently has been making temperature maps of planets, and this is something that was really unanticipated that we'd be able to do. And so this video shows measurements of the emitted light from a planet while it makes a complete 360-degree rotation. So if you can see the video playing in the top left corner, you see what we call the emission spectrum of the planet. This is measured relative to the host star, but as the planet rotates, it has a permanent day and a permanent night side. And so the day side, when it rotates into view, we can take this spectrum and we can detect the signature of water. So we can use that to measure the global water abundance of the planet. And then we can also, in the top right-hand corner, invert the data and measure the thermal structure of the planet's atmosphere. That is, how does the temperature change with pressure or altitude? And so what we've done now is made this global thermal map of the planet. How does the temperature vary with longitude and with altitude in the planet's atmosphere? And this allows us to study planetary atmospheric dynamics in a very new regime. This planet is highly irradiated by its host star. It's very close. And you can see the temperatures are much higher than what we see in the solar system planets. Instead of roughly 100 Kelvin for Jupiter, we are upwards of 1,500 or 2,000 Kelvin. Looking forward, the exoplanet community is very excited about the James Webb Space Telescope. And so the last slide shows measurements in the top right-hand corner that we've been able to make for a so-called super-Earth planet. Now, these measurements revealed clouds in the planet's atmosphere, and we weren't able to penetrate into the lower parts of the planet's atmosphere and reveal its composition. But it's interesting to point out that these were the first observations of a planet beyond our solar system that was sensitive to the atmosphere with an Earth-like composition. And so, looking forward to JWST, with the improved precision we'll be able to get, if we can improve the precision just a little bit, the bottom right-hand figure shows the expected spectrum of a true Earth analog that we could measure the spectrum of with JWST and detect things like water in the atmosphere. So it's very exciting to look forward with what we can continue to do with Hubble over the next few years, and then potentially probing habitable planets' atmospheres with JWST.
Great, thank you, Jacob. We've talked about planets and exoplanets in our galaxy. Now we're going to go way, 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 way out to an undiscovered country, right, that we're discovering. Hubble's very deep surveys going to the limits of what Hubble can do. And Dr. Jennifer Lotz, an astronomer here at the Space Telescope Institute, is head of the Frontier Fields program, which is using nature to help out in searching for the farthest objects we can see in the universe. Jennifer?
Thanks, Ray. So exceptionally deep images with Hubble have continually pushed the frontiers of human knowledge. A series of deep fields taken with Hubble over the past 20 years, with each generation of Hubble's cameras, has allowed astronomers to probe the star formation history of the universe over 95% of its lifetime. So if you go to the next slide, the first of these was the Hubble Deep Field, taken shortly after the corrective optics were installed in Hubble. A few years later, the Hubble Deep Field South was taken in an area in the southern sky. These images, you can click the next, things. These images in visible wavelengths are able to detect light from galaxies that is 4 billion times fainter than what the human eye can see. If you click next, yes, with the next camera installation of the advanced camera for surveys, the Hubble Ultra Deep Field was taken with a larger area and in a region of sky where the deepest X-ray images were ever taken with the Chandra X-ray Observatory. And if you click next, with the final servicing mission and the installation of the Wide Field Camera 3, infrared versions of the Hubble Ultra Deep Field were taken in 2009 and 2012. Yeah. You can cycle through all those again. Yeah. Okay, next. So these very deep images act as time machines for astronomers. And this is because the speed of light is finite. So as we look further out into the universe, we're seeing galaxies as they were 5 billion, 10 billion, 13 billion years ago. And that allows us to map the history of the formation of stars and galaxies, and even to try to push into the era where the first galaxies were formed. So if you click next, even though those images are very deep, surprisingly, the best candidate we have for the most distant galaxy was not taken in one of those deep fields. And that's because it was in a field that was strongly lensed by one of nature's telescopes. So this gravitational lens was able to boost and magnify the light from this galaxy that appeared something like 400 million years after the Big Bang. So if you click next slide. So, a few years ago, the challenge was put forth, can we peer deeper into the universe than the Hubble Ultra Deep Field with the Hubble Space Telescope now, before the launch of the James Webb Space Telescope? And, following on the results of that very exciting, very distant galaxy, astronomers said yes. And if you click to the next slide, the answer was to use nature's telescopes, to use these gravitational lenses to probe deeper into the universe than ever before. So 6 very massive clusters of galaxies were chosen to be part of this new Frontier Fields program, which is happening now using Hubble in concert with the Spitzer Space Telescope and Chandra Space Telescope. So if you click next, we're basically using Einstein's theory of general relativity that says that massive objects like clusters of galaxies bend and warp space, and they act as telescopes, magnifying and stretching the light of distant galaxies behind those clusters. And so by combining the power of Hubble with very deep imaging with these natural telescopes, we really are able to see deeper into the universe than we would without these foreground clusters. So next slide. This beautiful image is our first frontier field, Abell 2744. A lot of the red, yellowish objects are the cluster galaxies. Astronomers are very interested in the galaxies that are behind that cluster. If you go to the next slide. But what we need to do is to understand the optics of this cluster, and we need to make a map of the dark matter. And it's really just along very small windows in that image, it's the reddest regions, where background galaxies are magnified by factors of more than 10 up to 100. And it's in those very small slivers that we're getting the deepest view yet of the universe. So that's why we have 6 frontier fields and not just one. The areas covered in any given field that go that deep are very small. If you click to the next slide, already though this first cluster has yielded the intrinsically faintest galaxy ever seen at these very early times, so within 500 million years of the Big Bang. And astronomers are studying these objects to get a better understanding of the progenitors of smaller galaxies like our own Milky Way. If you go to the next slide, these data aren't just useful though for studying the very distant universe. They're actually revolutionary in understanding the clusters themselves and the unseen matter within those clusters. So the lens galaxies allow us to map out the dark matter within clusters to unprecedented resolution and precision, giving us new insight into the nature of dark matter. And then finally, I want to touch on something very exciting. If you go to the next slide, there's always with Hubble and all observatories, the opportunity to discover the unexpected, something that we didn't set out to do. So this is the 3rd frontier field, Max 1149, and just as we started observing it last November, a team of scientists who were searching for supernova found not just one supernova, but 4 images of what turned out to be the same supernova. So you can see in that inset 4 little yellow dots in the arm of a spiral galaxy that has been lensed by one of the cluster galaxies, that red object in the center. So if you go to the next slide, this is one supernova very far away, which exploded 9 billion years ago, but its light is being bent through multiple paths through this cluster. So there are 4 images appearing now, and each of those supernova light curves are offset by a few weeks. But the amazing thing is that this galaxy that the supernova was in is imaged in 2 other places as well in this cluster image. And so we think that the supernova appeared something like 20 years ago on the other side of the cluster, and we expect that this supernova will appear again sometime in the next 5 years. So just to conclude with my last slide, Hubble is truly operating at its peak, and with some clever ideas and a little bit of luck, we're able to do things that really are groundbreaking and unexpected, and we're making new discoveries of the distant universe. There are 2 more frontier fields to be observed in the coming year, and I'm quite sure we'll be watching this one cluster to look for the reappearance of that supernova.
Great, thank you, Jennifer. Our previous speakers alluded to the fact that Hubble, in a sense, has served as a pathfinder for even more powerful and deeper observations of the far universe and exoplanets. So Dr. Jason Callery, who's our project scientist here at the Institute for the James Webb Space Telescope, will give us a look into the future, how Hubble's going to work with 2 powerful observatories under construction and one on the drawing boards. Jason?
Okay, thank you, Ray. It's a pleasure to be here. I'm very excited about using Hubble over the next few years to tackle exciting problems in astrophysics, but I'm even more excited about using Hubble in concert with future technologies to open new scientific barriers. So if we go to the next slide, as the previous speakers have alluded to, Hubble's scientific reach spans all scales, from making new discoveries and studying objects within our own solar system right here in our backyard, to witnessing the life cycles of stars by capturing these rare images of individual stars at different states of their evolution, figuring out how galaxies come together and grow over cosmic time, to looking at these glimpses of the distant universe, as Jen just alluded to. And so if we go to the next slide, astronomers over the last 15 years have been thinking about what new technologies we need to pair with Hubble to expand our scientific discovery into new regimes. And through processes that have included thousands of astronomers writing down what they see as the top scientific challenges, we've come up with two new technologies. And so one is a telescope that's more powerful than the Hubble Space Telescope, and that's the James Webb Space Telescope. And the second one is a telescope that can see a much bigger part of the universe than Hubble can, and that's the Wide Field Infrared Survey Telescope, WFIRST. And so there are many different science examples that you can use to show how these facilities will expand Hubble's reach into new dimensions. But I think the deep fields example that Jen gave is an excellent one. So if we go to the next slide, you can see this beautiful movie that the group here at Space Telescope Science Institute put together that helps put our deep field into context. And you really get a sense here that it's where other ground-based telescopes and large telescopes hit their limit is where Hubble really starts taking off. And Hubble revealed through the single image 10,000 galaxies in a tiny little patch of sky. But Hubble not only tells us how many galaxies there are in this image, and therefore how many galaxies there are in the universe, but it helps us understand how these galaxies fit into the overall cosmological context. And so one of the things that astronomers have realized by looking at this image is that the earliest galaxies that we find in this image are have light that appears already mature, and so they're not indicative of the universe's first galaxies. So if we go to the next slide, one of the pillars of the science goals for the James Webb Space Telescope is to find those first galaxies. That first light in the universe represents the seeds of everything that we have today. It's when the dark matter of galaxy halos came together. It's when the metals were first created in galaxies, and then through the first stars sprayed and spread out into the universe. And so it's really an anchor to our entire understanding of how the universe transitioned from this dark, almost boring place to this beautiful lit up universe that we see today, filled with stars and galaxies and light. And so the James Webb Space Telescope is designed to witness that epoch when the universe transitioned between those two regimes. Again, if you go to the next slide, if we look at this image again and put it into the context of the WFIRST mission, you know, one of the things that Hubble tells us about this image is that often the most interesting objects in the deep field are the few and rare highest redshift galaxies. We have one redshift 10 galaxy in this image that gives us some idea of what the early conditions of galaxies were in the universe. And so if we go to the next slide with the WFIRST mission, what we'll end up doing is expanding the reach of this image tremendously by serving a bigger volume of the sky. And so this is an example of how big that image actually is relative to the full moon on the night sky. And so if you go to the next slide, where that one single Hubble image had 10,000 galaxies and one redshift 10 galaxies, a typical image from the WFIRST telescope will contain 1 million galaxies. A similar deep field will contain 1 million galaxies. And so where you have one redshift 10 galaxy, you'll have 100 redshift 10 galaxies. And by opening up that part of parameter space, and for the first time taking images of the night sky with a wide field of view camera that also operates at high resolution, you open up your discovery potential to find even higher redshift galaxies that are going to be more rare and we simply happen to miss in the Hubble Deep Field. So if we go to the next slide, you know, ultimately, the Hubble Space Telescope has been tremendously successful because it's not only opened up new discoveries and brought things that were in the realm of science fiction into reality, but it's also become the most powerful telescope to characterize objects in that new astronomical landscape through its servicing missions. Hubble has made discoveries, and then the new technologies and cameras on Hubble have made it the most powerful thing to figure out what those discoveries are telling us about the universe. And so this is a snapshot of the science motivation that astronomers wrote down for each of the James Webb Space Telescope and the WFIRST mission. But to me, these science quests are analogous to the science case of the Hubble Space Telescope as it was written down in the 1970s. The scientific discovery potential for these two telescopes is huge. And they will have their own new discoveries and change that astronomical landscape once again. So Tony, if you go to the last slide, when that happens and that landscape changes, we have to recognize that these two facilities are both infrared telescopes, and so the only type of light that they detect is infrared. And the most exciting science comes from finding out what those objects are telling us about the universe. And in that era, Hubble will be the only game in town that can see both ultraviolet and visible light. So I think the Hubble Space Telescope's future in the James Webb Space Telescope and W1st era is brighter than ever.
Great, Jason, thank you. I'm really pleased with these discussions. It's hard to compress 25 years of discovery into half an hour, but our guests really touched on some of the really big discoveries of Hubble, excitement in past discoveries, and the tremendous promise of the future with space telescopes. With that, let's open the line to reporters. Please state your name and affiliation, and address your question to a specific researcher, unless you want a more general question for our entire panel here. Okay, so we're ready for our first question. We're ready to take questions from call-in.
Is the line open?
Your first question comes from Alan Boyle from NBC News. You may ask your question.
Hi, I think this question would be directed to Ken. You mentioned that there would be at least 1 to 2 years of overlap, I think, between James Webb and Hubble, and that the combination of the two observatories would be very powerful. Could you give an example of how those two telescopes would work together, maybe something that illustrates how those complementary approaches are more than the sum of their parts?
Well, I think as you just heard, Jason and Jennifer and Jacob gave you some excellent idea of what Hubble is doing now with exoplanets and distant galaxies. I think those are clearly two areas where having both the ultraviolet and optical power and abilities of Hubble complement very nicely those of James Webb. So, for example, in the transiting exoplanet spectra, to be able to take both the optical and the infrared spectra at the same time gives you far more information than you would have just by understanding one chunk of the spectrum alone. And Jacob's certainly more competent to describe all of the benefits there than I, but it would seem to me that in that particular case, if you're trying to characterize a planet's atmosphere, especially a planet that's something like that of the Earth, you really do need multiple band passes. In the case of finding distant galaxies, most of these distant galaxies are shifted into the infrared. One of the most important things Hubble can do for you in that particular case is not see the galaxy. And so the fact that you don't see it in the optical means that the object is in fact very distant, and that the light is shifted into the infrared because of the expansion of the universe. Whereas if you had seen some light with Hubble, it may be a very red object masquerading as a distant galaxy. So that's just two very simple examples, but there are a whole host. And I think, as I alluded to earlier, the possibility of following up one observatory's discovery with the other observatory is a way to provide additional information and immediate insight into what it is that you've just found. Hubble has for years been the go-to observatory when other observatories make discoveries. Everybody wants a Hubble image or a Hubble spectrum to follow up, because the information from Hubble is so complementary to that from the ground. I think the same will be true in the James Webb era.
Jason, did you want to add?
No, I think that's a great answer.
Okay, great. We're ready for the next question.
If you'd like to ask a question, please press star, then 1. Record your first and last name clearly. One moment. We have no further questions.
Okay, we'll go to people here in the room. Let's see. Chris, do you have a question?
Yeah.
I'm sorry. Chris Gaynor was writing a history book on Hubble under contract to NASA.
Well, I'll ask something of a bit more current interest. I was sitting in at the session this morning, and we heard a lot about the planetary astronomy, our own solar system, and starting to look at other ones. But within our own solar system, and I guess this would go to Dr. Simon, what areas are going to be looked at quite a bit in the next 4 or 5 years with Hubble?
So one of the projects we have planned with Hubble is called the Outer Planets Atmospheres Legacy Program, and we will be taking global maps of the 4 outer planets, 2 global maps every year until the end of Hubble's lifetime. And the idea behind this is that it gives us a better chance to understand the weather on the planets. What we have right now is sort of the equivalent of looking at the Earth once a month or sometimes less, and then trying to determine what's happening on the whole planet with weather with only that information. And so what we wanted to do was have a more regular and frequent program where we could actually watch for changes and look at a complete global 2-dimensional wind field across each planet and start to understand those circulation patterns a lot better. And so that's one of the things that we have planned that will go from now until the end of Hubble's lifetime. So you'll see a lot more images coming out of for the outer planets over the next few years.
Okay. Do we have any other call-in questions?
We have no further questions at this time.
Okay, let me go back to the room here. NHK TV? Yes.
This is a question for Dr. Lutz. I'd like to know what's the original Hubble deep field? What's the impact of the project on the series of the deep field initiatives later on? How did it change our view of the early universe?
Well, I was in college when I saw that. I was majoring in astronomy, and I was reading, I don't know if it was Physics Today or Scientific American. And it's transformed the way that we study galaxies and understand the origin of our own Milky Way. People didn't know before Hubble stared at one patch of sky for 10 days. That there would be so many galaxies that would be visible, that there were thousands within a very small patch. So with that one image, we could quickly figure out that yes, the universe was filled with galaxies. And not only that, we could study them, we could see them, and we could start to use those images to understand the history of the formation of stars and other galaxies. So that was very powerful. And I would say much of the work in galaxy evolution over the last 20 years has been inspired by that image.
Thank you.
Okay, any last questions here? Oh, go ahead, Chris.
Well, maybe I'll ask one more. I think probably for Dr. Sembach, but the universe as we see it today is quite a different place from what we saw 25 years ago when when people were flying down to the Cape for that launch. Do you want to just try and tackle that question? How does it look different today from 25 years ago?
That's a great question. I think the universe is a lot more colorful today. It's certainly a lot more dynamic. Things change. We can watch them change. We have watched them change, whether it's the planets in our own solar system or stars coming and going. I think that it's a much bigger universe than it was 25 years ago, in the sense that we really do know there are a lot of galaxies out there. I feel a lot smaller than I did 25 years ago as far as location in the universe. I think even 25 years ago, there was a great sense of wonder as to what we were going to see. But I think one of the powerful things about Hubble has been its continued ability to inspire wonder in people. And so, we should continue to operate this telescope until it stops inspiring wonder. And I suspect that's Not on the immediate horizon.
Right. So, can I build on that a little bit? So,
Yeah, sure.
I know that in tying together the previous question and this question, the previous question was about the astronomy impact of the deep field, and this one is similar. But, you know, really, you know, there have been a few times in our history where, you know, our view of the universe and our answer to the question of what our place is in the universe has been completely overthrown. You know, we were very special, right? We were the center of the universe 2,000 years ago. And that remained the model that we had up until a scientist used a telescope and pointed it to the sky and showed that, you know, in the case of Galileo, that wasn't the case, and it was unlikely that the Earth was the center of our solar system. And then a few hundred years after that, it took a scientist by the name of Edwin Hubble with a telescope, a 200-inch telescope at Mount Palomar, pointed up at the sky and looked at these faint little smudges that we see in the night sky and showed that those smudges were not a part of our galaxy, but were entire galaxies themselves, and therefore we became a little bit less special. And so with respect to the deep field, I think it, you know, represented this, you know, this ultimate, you know, answer to what is our place in the universe by showing that, you know, we're not special at all, that we're, you know, that we're sitting on a rock that's orbiting a star, and that star is one star out of 100 billion in our galaxy, but that galaxy is one galaxy out of 100 billion in the universe. And so I think Hubble's, you know, legacy on our world and our culture has been answering that question of what our place is in the universe.
I'm going to jump in strictly from a public opinion point of view. The 60s, 70s, well, the 60s were going to the moon. 70s and 80s were the spectacular exploration of the solar system with the NASA probes and European probes. And they presented to the public a whole new solar system. I think with the launch of Hubble, we extend that to the entire universe. I think astronomy was, deep space astronomy, at least, and I've written about this for a long time, a little more staid, but when Hubble went up, just crazy, colorful things just started coming out of the woodwork. So I think it's done for the universe what solar system exploration did for the planets in the 70s and 80s.
Can I build on that a little?
Yes, I knew I was just setting you up.
Well, I think that's true, but, you know, we got these interesting pictures from Voyager in particular as it flew out to the outer planets, but it was only a flyby mission. And so we got a very static view even of the solar system, where Jupiter was really orange, Saturn was the yellow one, the other two were kind of boring and blue. And really, Hubble was the next big thing to look at the solar system, and almost shortly after its launch, you know, after the adaptive optics, corrective optics were put on, we had this big impact of comet fragments into Jupiter. It kind of woke us up again to this idea that even the solar system is very dynamic. Things are happening real time, all the time, if you just look. And, you know, we hadn't launched those missions out again to Jupiter and Saturn when Hubble was up. So I think Hubble really expanded that for the solar system again as well.
Yeah, that's a good point. Okay, anything here? And I think we've used up our telephone time. Well, with that, I want to thank everybody for taking the time out from this conference to reviewing some of the key discoveries with Hubble. This event will be available as a recording and also broadcast on YouTube. And again, thank you all for coming and participating. Thanks to our reporters for joining us today. Okay,
This
thank you.
concludes today's conference. Welcome to the Hubble Science Legacy Teleconference. At this time, all participants are in a listen-only mode until the question and answer session of the conference. At that time, if you would like to ask a question, you may press star, then 1. Today's conference is being recorded. If you have any objections, you may disconnect at this time. Your host for today's conference is Ray Villard, News Director of the of the Space Telescope Science Institute. You may begin.
Well, good afternoon, everyone. Greetings from the Space Telescope Science Institute in Baltimore. On behalf of everyone here, I'd like to welcome our reporters to the Science Writer Telecon, Hubble Science Legacy through 2020. Over the past quarter century, Hubble has probed the universe both near and far, and has unveiled wonders that were once only left to the imagination. Besides being a scientifically productive observatory, Hubble's discovery this way, and your slides are all queued up. Tony's doing double duty streaming on YouTube. We have a separate teleconference line with the NASA Teleconference Center.